Salutations, chemists. We're going to talk about buffers. You've already learned a little bit about buffers. Buffers are a solution that resists changes in pH, and you have several different buffer systems in your body. Buffers play a really important role in industry and food processing because we have to maintain the pH for things, and sometimes it has to be maintained at very different levels. We need a pH very low in like our stomach and digestive systems, but a pH much higher for our blood. So we want to talk today specifically about how buffers work, and not through a simplified cartoonish model, though I do think that's really helpful to start our understanding. We want to really get into a little bit more of the nitty-gritty details, and that's going to take us back to equilibrium, reaction rates, collision theory, and Le Chatelier's principle. Buffers is kind of like all of it. So a buffer is created from a weak acid and its conjugate base, or a weak base and its conjugate acid. You get the idea. It's these pairs. So for example, a buffer can be made by carbonic acid and hydrogen carbonate, also known as bicarbonate. Now, if I asked you to go and make this buffer for me and you went and found a solution of carbonic acid, that's this one right here. Where's my mouse? The mouse is missing. There it is. And then you would have trouble finding this in the lab, and that's because you actually can't have a sample of that's just this negative ion. Our solutions, our samples, our salts are always neutral. So a lot of times it's actually more like this. Okay, here's another example of a buffer. The buffer is made by mixing phosphoric acid with sodium dihydrogen phosphate. Don't worry about those names, I'm just sharing with you. Now, sodium doesn't play a role in the buffer system, but it's kind of like the wingman that brings along the conjugate that we need. So you'll notice these are conjugates. They differ in only the presence of a hydrogen ion, and they have a weak relationship, and that's really important. A strong acid or strong base can't make a buffer because we need reversibility. So another way we could say that buffers are made or define buffers is it's a solution of a weak acid or base and the salt of its conjugate. Because we are going to have to mix a salt to make that buffer because we need a positive bringing along that anion. So you'll see it defined that way as well. So what about this? If we were going to make a buffer out of acetic acid, which is the acetate ion, you might recognize it right there, covalently bonded to a hydrogen, what would we want to mix it with? So we'd want to mix it with the salt of its conjugate. So if that's a weak acid, what's its conjugate base? Its conjugate base would be acetate, C2H3, O2. And then of course a negative charge, but we're going to put it with a neutral. We could put like a sodium with it so that it's a +1, -1. Pretty much any salt of acetate would work. So sodium acetate is the example that I chose. So let's take that example. Let's say we mix acetic acid with sodium acetate in an aqueous solution, and we let them reach equilibrium. So we're going to express that equation this way. So this is another way to write acetic acid that kind of biologists tend to prefer, or organic chemists. It's because it shows you a little bit more about the structure than the other format that we just looked at. So I always think of it as CHQ. So CHQ plus water, equilibrium, makes hydronium and acetate. So that's the equilibrium that's going to get established. So let's just do a little review and identify who's behaving as a Bronson-Lowry acid and who's behaving as a Bronson-Lowry base. Now you might know already just from some of the names I've been mentioning, but you should be able to, identify that in a problem by tracking the hydrogen. So if you look here, you'll notice a hydrogen is missing on the product side, which means it got donated, right? Got donated here, which is how this one goes up a hydrogen and this one ends up down a hydrogen. So acids are our proton donors and bases are our proton acceptors. So that's our acid and our base from the Bronson-Lowry theory. So in reverse then, who behaves as what? Well, in reverse, the hydrogen has to be donated back here. So here, let's say this is our conjugate acid. We'll do Ca, since we want to distinguish it from our acid on the reactive side. And since this would be the acceptor of this proton to turn back, going back on the reverse reaction, this would be our conjugate base. So we have a reversible reaction that's reached equilibrium between these acids and bases. But of course, the equation can be a little bit misleading. What's really going on, if we could see it at the particle level, might look something a little bit more like this. And so I've used those same A's and A and CB to identify our acetate. So this is acetic acid, and this is that acetate conjugate base, and then water and hydronium in the solution. So we really have a mixture of all of these. Now, technically, we also have hydroxide present, right? Because we would always have some hydroxides in any aqueous solution. But just for the simplicity of the diagram, I've left them out, but should know that they should be implied. And if we were going to determine the pH of the solution, what would we want to think about? Well, we want to think about the hydronium ions, right? It's the hydronium ions, and I have 4 of them right here, that determine pH. Remember, pH is negative log the hydronium ion concentration. It's actually not about how many of these we have. It's not about how many molecules we have in the acid form. It's about how many hydronium ions we have per liter. So I want you to pay attention to those 4. Now, notice these 2 right here. I got a water right next to a conjugate base, and which is these 2 reactants. So I want you to think collision theory, because of course these molecules aren't static, they're in solution, they're moving around. So it's totally possible that they're going to bump into each other, and we're going to have that forward reaction occur. But of course, in other places, we're going to have the reverse reaction occurring right here. Hydronium bumps into the acetate ion and donates the proton back, right? And so what we really have going on then in our equilibrium solution, is that both reactions are happening. They're just occurring at an overall rate that doesn't result in any net change to the system. But what if we add HCl to our example? Now you should be able to identify HCl as a strong acid. So we know that by adding HCl to our solution, it's going to react 100% with water, which would increase the hydronium ion concentration. If you need to see that reaction, HCl plus water, it donates. This is a non-reversible because it's a strong acid to make hydronium plus the chloride ion. Now, shouldn't that change the pH? Shouldn't that cause it to decrease if pH measures the concentration of hydronium? Well, we know it doesn't because we're talking about buffers, but why not? Well, let's go back to our slide here. So let's say I dump in some HCl. The effect of that is going to be to increase my hydronium ion concentration. Now you don't need to worry about the chloride ion. It's technically there, but it's just a spectator ion, meaning it doesn't participate in the chemistry of this reaction. Now I would think that adding more hydronium would change the pH, since that's what pH measures. But let's think back to reaction rate and Le Chatelier's principle. What happens when we increase the concentration of a product? When we disrupt a system at equilibrium, we disrupt the rate at which these reactions are happening. So our reverse reaction is going to be happening faster or more often than our forward because there's more of them. There's more of them to be present. So if my first reaction happens faster, it's going to be winning for a while until a new equilibrium is reached. So the way we say this with Le Chatelier's is that by increasing the concentration of our product, we shifted the equilibrium composition to the left or toward the reactant side. But in shifting it to that, what did I use up? What had to react? I had to use up hydronium. Now at my new equilibrium, which of course would actually be, these moving back and forth and changing, but at my new equilibrium, look at how many hydronium ions I have. I still have 4. The pH has not changed. So let's return to this. Shouldn't that change the pH? Nope, it should not. And the reason for that goes back to Le Chatelier's principle. The increase in product concentration, so in this case, we increased the concentration of our hydronium, cause the reaction to shift toward the reactant side. So that means shift to the left. And in doing that, it used up that excess. So even though we increased the hydronium ion concentration, in the end it stayed the same because of that shift in the direction that used it up. And this is all because we have a reversible reaction between the conjugate acid and the base, or the acid and the conjugate base. Well, what if we add sodium hydroxide to our buffer example? So you probably recognize sodium hydroxide as one of the strong bases. All the hydroxides, the metal hydroxides, are strong bases. So that means they 100% dissociate to produce hydroxide concentration, to produce the hydroxide ion. Shouldn't that change the pH? Now you might be thinking, well, pH isn't a measure of hydroxide, so maybe not. But remember, there's that inverse relationship. If you increase the hydroxide ion concentration in an aqueous solution, we would expect a corresponding decrease in the hydronium ion concentration, since the product of these two is always the same, the equilibrium constant for water. So I should expect a change in pH, because I should see this becoming less common. But if we think about it in terms of Le Chatelier's principle, by adding sodium hydroxide, I put in this product here. Now, you'll notice that chemical species isn't in my chemical equation, so maybe we feel like a shift wouldn't happen. However, remember how incredibly favored the reaction between hydroxide and hydronium to produce water is. And if you're wondering how do we know that, remember the equilibrium constant for water is so incredibly tiny for the ionization of water, and that's for, you know, the water breaking apart to make hydroxide and hydronium. Well, if that number is so incredibly tiny, that means that this reaction is not favored, but this one is, or sorry, I said that backwards. This one's not favored, the water breaking apart isn't, but this one is highly favored. So what's going to happen when we put that sodium hydroxide in there is that these hydronium and hydroxide ions are going to react with each other very, very quickly to create water. So we've done two things there. We've actually decreased the concentration of hydronium and increased the concentration of water. So we've decreased a product and increased a reactant concentration. Well, according to Le Chatelier's principle, that's going to shift in the direction to replace the lost product and use up the excess reactant. Or if we want to think of it in terms of the collision theory, we're going to have a lot more collisions between our acids and water because there's just more of them. It's just a statistics thing. So what's going to happen then is that we're going to have an increase in that forward reaction for a while, you know, going back and forth until a new equilibrium is reached. When that new equilibrium is reached, we're going to notice it created more of this than we had before. So that's why we say it shifted in that direction. So if I count my number of hydroniums, I'll see I'm at 4 again. So the pH then has not changed. So if we add sodium hydroxide to our buffer, we dissociate to produce hydroxide, we'd think there'd be a change in pH, but nope. Nope, nope, nope. And the reason being, hydronium reacts with, hydroxide, reacts with hydronium. That's a really favored reaction. I'm going to put an exclamation point because it's so favored to make water. This results in a Le Chatelier's shift. We have actually done two things. This says we decreased in product concentration, but we also, I'm going to add this, increased a reactant concentration. So we have two things that favor a shift to the right toward the product side. So in doing that, the reaction shifts in a way to replace the lost hydronium. So buffers work on the basis of Le Chatelier's principle, also known as the law of equilibrium. If you have an equilibrium between an acid and a base, between something that can accept a proton and something that can donate a proton, adding acids and bases can, as long as you stay under the buffer capacity, can minimize pH change shifts. If you add an acid, we shift that way to use it up. If you add a base, we shift that way to replace the lost acid. And that's buffers in a nutshell.